Heidi ho, more window function goodness ahead. Alright, so we had window functions in the form of aggregate functions. We had window functions in the form of lag and lead that allow us to explore the rows around relative to the current row, around the current row. And then there is this particular group of window functions, the first, last, and nth value window functions, which are again different. They allow in-frame row access. So once a frame has been built, it makes sense to speak of the first, the second, the nth, and the last row in a frame. And the window functions listed at the top of this slide let you do exactly that. Access the first, the last, or the nth row in a frame. This is different from just looking around the current row. Now you have positional access inside the frame. Okay, and that really can make a difference. So let's see how that works. So this would be the syntax that is being used here. We will of course have a window specification here, and in this case, unlike lag and lead, in this case the frame specification will be important again. So it's not only about the current row and its vicinity, it's about the entire frame of rows that has been identified in the current sliding window. Of course, the current row is part of that frame, and we could use one of these functions here to access the current row, but this is not the point. It's the point to have arbitrary access at will, positional access at all of the to all of the rows inside the current frame. This is different, for example, from the aggregates that we've discussed before. Aggregates will just walk over all rows in the frame and perform their aggregation job. This is not what we do here. We access individual rows, single rows, using these first, last, and nth value window functions. Once we have accessed the first or the last or the nth row in the frame, we will then evaluate expression E for this particular row. Okay, right. So, and of course, this will yield a value. The evaluation of E for the first row or the last row or the nth row in the frame will yield a value. This is the value of the entire window function. Okay. So let's see. Of course, there's restrictions again. So we may not reach outside the current frame using these functions. This is of course completely impossible for first and last value. They are of course bound to the frame boundaries. But with nth value, we could imagine to reach for the nth row in a frame that only has n-1 rows. Excuse me. And this is of course impossible. In this case, we will get a null value returned. So accesses outside the current frame will lead to null values. A picture is worth 1,000 words, so let's do that. So this is a situation of in-frame row access. Of course, we are looking at the base table. Of course, it has been ordered according to ordering criterion. Let that ordering criterion be A or any other ordering criterion. That's fine. Okay. Then there is the notion of the current row, and the window function that we're working with is defining a frame around that current row using between and following, preceding, and so on. All of these keywords. We will see examples in a minute again. Okay, so let's assume that this is indeed the frame around the current row. It's a 5-row frame. Okay, in that frame, thanks to the well-defined ordering on the table, there will be a first row, and with first value, we could evaluate an expression that I've omitted here, just indicated via a dot. We could evaluate an expression as if it would be evaluated for this one particular row, in row 2. With last value, we could evaluate this expression here, as if it were evaluated for row 6. Okay. Right. Nth value will give you access to the row that is at offset 2 or 3 or 5, whatever you specify in the second argument to nth value inside the frame. The first row in the frame is at offset 1, so you see that this equivalence is holding, and first value is actually syntactic sugar for this slightly more complicated expression. Of course, reaching outside the frame will lead to a null value result. All right, so there is no sixth row in this 5-row frame. Reaching outside beyond the frame in this case will yield a null value. Okay, I think this is simple enough. I've brought an example to play with me in the sample file, in the SQL sample file, the window functions file that we've used so often already. Here you can see I'm iterating over our playground table again. For reference, here's the playground table. A column, B column, used for partitioning and so on. Partitioning is no issue in this particular case. It's all about the framing. All right, so we establish a well-defined order on the rows in this table W, and then establish indeed a window that could contain up to 5 rows. The current row plus 2 preceding and 2 following rows. Of course, at the fringes of the table, at the borders of the table regarding the ordering criterion on column A, there won't be 2 preceding or 2 following rows, and the windows will be smaller. Okay, we can see all the rows contained in the window using this array function, and we have done that before. But of course, the focus is on the first, the last, and the nth value calls here of these window functions. You see, all refer to the same window. We will, of course, see the first and last value in these frames, and there's also an nth value access to the second row in the frame. All right, I think this is all there's to it, so let's go. All right. So 9 rows in the example because 9 rows have been part of the playground table. Okay, so each of the rows is the current row at one particular time, as you can see here. Around these rows, we are establishing row frames of a maximum of 5 entries. You see none of these frames indeed contain more than 5 rows. That's what we expected. And at the fringes, there might be less than 5 rows. So for the current row, row 1, there is no preceding rows. For the current row, row 9, there is no following rows. All right, so these are the windows, and these are the first and last rows in the windows. Finally, we've got access to these using the first and last value window functions. We can also look at the second row inside the frame, which is the nth value with second argument 2 here, and this would be the second row in the frame. Okay, sometimes, as you can see, the second row might be the current row as it happens. Okay, this is, I think, simple enough. This is nth value, last value, first value. Okay, so what can you do with that? Again, you can establish context around a current row. You can establish a frame around the current row, and then use the functions first, last, and value to explore the context, the vicinity, the neighborhood of the current row in a well-defined order. So maybe you recall this particular rendition of a simple map that we've used so often. We've stored it in table map in this table that stores the x-coordinates and the altitude at particular x-coordinates inside a simple 2-column table. Okay, so what we would like to do now is to perform a walk across this hilly landscape and identify landscape features like, hey, this is a peak, I think, and this would be a valley, and oh, here's a peak again. I would like to identify such features. All right. Sometimes there are some interesting features. For example, here in the lowlands, there is no interesting, this would be a valley. Okay. So in these lowlands, this is nothing of interest. So there's nothing to see here, and we would like to indicate this with this minus sign. But sometimes there is memorable features of the landscape. I would like to identify these. Relative altitude changes is what is playing a role here. Okay. So one strategy to implement this in SQL using window functions would be to record the altitude changes or look at the altitude changes in a sliding window around the current X position. So we would shift the current X position across the hilly landscape, across our map table, and then establish, in this case, a window of size 5 with 2 preceding and 2 following rows inside this window. All right. And the current row would then be always at the center. This would be the current row at the center of this window. And then we would look at the altitude changes around that current center. So it goes, the altitude changes, the altitude goes down here until we reach the center, then altitude goes up again. I think this would characterize this current row, this X position, as a valley. It's the same for this. The valley is not as pronounced, but it would still be considered a valley. This would be a valley, I think, and this would be a particular valley also. All right, so these would be valley features, and of course we could also identify peak features as you see down here. All right, so there would be multiple sequences of altitude changes that we would consider valley or peak occurrences in our landscape. Okay, so to make the detection of these altitude changes a bit more efficient in our queries, so a bit more simple to express, we will simply map such altitude changes like this, down, below, down, low, to these ASCII character sequences. So 5 points in this frame of size 5 will lead to 4 altitude changes between these 5 points. So each of these windows of size 5 will map to character strings of length 4 that characterize the altitude changes that we've seen, like down, even, up, down, down, even, up, down. Okay, so that would be the string that characterizes these altitude changes. Okay, once we are at this point where we have mapped the altitude changes in our landscape to these string encodings, we could simply use pattern matching, regular expression matching on these strings to identify situations where that we would characterize as strings and as peaks and valleys. Okay, so I think let me check. Is there anything else to explain? Yeah. So let's have a closer look at how we detect or how we would compare these altitudes and detect changes. So if we zoom inside one such window, this would be one such window of size 5. And of course, this would be the current row. Okay, so if this is the case, then of course we could easily access the altitude of the current row, no problem about that. But we could also access all the other altitudes easily inside the current frame. We could just use the first and last value, for example, window functions, to access the altitude at the beginning and the end of the frame. So if we evaluate the altitude or evaluate the altitude column reference inside this context of the first value or the last value function, then these altitude references would be evaluated as if they would be evaluated for the last row, respectively for the first row in the frame. So we would get access to the altitude here at the beginning or at the end of the frame. Likewise, we could access the intermediate altitudes here at the second or the fourth position in the frame. So we would have, using these accessors here, these window functions and the current row, we would have access to all individual altitude changes inside this window. And of course, if the altitude for the first entry in the frame is less than the altitude of the second entry, we would map that to an ascent in our string encoding. I think that's simple enough. So random access at will inside the frame gives us the possibility to easily perform such comparisons. Okay, so now that we can perform these comparisons, it's very simple to arrive at the wanted string encoding that we were talking about. Okay, yeah, well, we would just walk over the landscape, of course, in a left to right fashion again, and we would establish windows of size 5 rows. This is the frame. And it would contain up to 5 rows, as we've already seen in many examples. Okay, using this window W, all right, we would then use the window functions like first value or nth value to compare the altitudes at the particular points. So that would be the altitude at the very first row in the frame. This would be just the next row in the frame at the second position. We would compute the difference and record the sign, which would be -1, 0, or 1. And we would do the same for the second and the third row, which happens to be the current row, and the third and the fourth row, and the fourth and the fifth row. These are the 4 altitude changes that we planned to record. All of them have been expressed as differences here for which we record the sign. These are 4 times the integers -1, 0, or 1 that we've found here. To translate these into a string that we have shown on the previous slide, to translate these 4 sign changes or signs into these ascent and descent symbols is a very simple job to do. We could write a very simple SQL UDF to do just that. I've brought it with me. I can show you in the terminal once we switch over. And that's all to it. That is all there is to it. Whew. Okay, so we are left with the string encodings of altitude changes. We could then perform regular expression matching, simple string matching on these distinctive altitude change strings to detect valleys and peaks. Let's do just that. Okay, I think I brought an extra file with me. Yes, I did. Okay, so here's the definition of the map again. I don't think I have to show this again. This is the map we have seen so many times already. I think it's been defined a dozen of times already, so it's present in my database. All right, that's cool. Let's look at the UDF. A UDF that converts four integer signs, 4 -, 0, and 1 sign symbols into the corresponding ASCII encoding here, so that we then can perform string pattern matching on that encoding of altitude changes. Well, we would just use these 4 integers, the -1, 0, and 1 integers, pack them into one array, which we then unnest so that we can iterate over these integers. So that would be an iteration over exactly 4 rows. Okay, and well, we would use this array access here to map -1, 0, and 1 to the symbols found in this array here. Okay, all that was left to do is to aggregate these strings that we have extracted from the array into a single string, of course in the correct order, and that's the string that we will return. This is the textual string that comes out of it. So let's see whether this function behaves as expected. -1, 1, 0, -1. Okay, this is indeed what we've seen here. A descent, an ascent, I'm sorry about that, and a descent, and so on. Okay, so this is what we've encoded as a string here. So for these strings, we would then search using regular expression search. Okay, so let's see. Well, this is just the query that we've already seen on the slides. It's the conversion of the map in the according slope information. Okay, so we would just perform the walk over the map in the right direction using a 5-row window. Inside that 5-row window, we would access the individual altitudes, perform the subtraction, perform the sign computation, and convert these signs using our slope UDF that we've just seen into the text to string. So let's see what comes out of that if we just look at the slope strings that we have identified. Okay, yeah, looks good to me. So these are the slope strings, the ascent and descents, or even even landscape features that we have identified in our landscape. Okay, so that's all well and good. Nobody can read this gibberish of arrows. Let's translate this into distinctive peak and valley indicators. And that's what's being done in the second and already last step of this query. Let's reactivate it. Okay, so we would just iterate over this table of slopes, such a table here. So if we find a slope that looks like this, like 2 times up, 2 times down, like 2 times up, 2 times down. Yes, this would indeed be considered a peak according to this regular expression match. The slope similar to is just the regular expression matching function that is built into SQL. All right, so this simple regular expression is only looking for sequences of 2 characters that look like this, that are followed by 2 sequences, 2 characters that look like this. If we find such a pattern, then we indeed have found a peak in our landscape. All right, if we cannot match these patterns, then there is no distinctive landscape feature, and we just emit the minus here. And that's all there is to it. No window functions involved, just pattern matching. All the processing, all the heavy lifting has been done already in the first CTE here. So it's time to evaluate that. And there we go. There is indeed some peaks, some valleys to be found in our landscape. Okay. Let's briefly switch back to the slides again. Because I wanted to point to a particular feature, a super recent feature that has been added to SQL in the SQL 2016 standard, and it's the Match Recognize feature. All right, Match Recognize has been built, has been specifically built to identify patterns, to identify such features in a series of data, in a well-ordered series of data stored inside relational tables. All right, so Match Recognize would be very well suited to implement the use case that we have just manually implemented using window framing and pattern matching. All of this is implicitly built into the Match Recognize feature provided by SQL 2016. As you can see, such a Match Recognize is a rather complex construct that has been added to SQL, and indeed it's not supported in PostgreSQL right now. That said, I think I saw some developer discussion in the PostgreSQL community that indicates that there is some interest in bringing Match Recognize to PostgreSQL, but not yet. It's only implemented in Oracle as far as I can tell for now. Okay, let's see. So such a Match Recognize is a complex beast, and it comes, of course, with a clause that orders the rows inside the target table, and that's no surprise. Order is crucial for identifying and working over a table in a serious fashion, so in a left to right fashion or in a timestamp fashion and so on. So ordering is really important. Once data has been ordered, we can use so-called defines in Match Recognize to tag the rows, to tag rows with interesting, to tag rows that contain interesting bits of data inside our series of data. All right. So we can specify predicates that assign tags to rows. Once we have tagged all the rows, we can specify regular expressions over tags, not over text, but over row tags. And I identify patterns like if there is a row that has been tagged foo, followed by another row that has been tagged foo, followed by 2 rows that have been tagged bar, then something interesting is in this data. And we could then evaluate so-called measures for the match. We could record the location of the match, the length of the match, other features of the match. All of this could then be measured, and this would then make for the output of the Match Recognize clause. Very powerful, very interesting. I have sketched how the peak and valley use case that we have just seen in our sample file in an expression that uses Match Recognize. Okay. So we would, of course, iterate over our target table. In this case, it would be the map. We would then invoke the match recognize clause, okay? And all of the rest here, all of the rest is the super monstrous match recognize clause. Okay, so that's really a major addition to the SQL language. We would order the rows in the map table by their x coordinate, and this is something that we know already. We would then assign tags to rows. Here are 3 different tags that we could assign to rows. We would assign an up tag to a particular row if its current altitude is larger than that of the previous altitude that we've just seen. You see that there is functions like previous or successor functions which play the role of the lag and lead functions or the nth value functions that we have already seen in our previous discussions. Okay, so altitude changes that look like this would be tagged like this, and once we've identified or assigned tags to rows, we could then evaluate these regular expression patterns. You see that these are patterns that are not specified over strings or text, but these are patterns that I defined over tag values, the tags that I've just defined below here. All right, let's not go into the details, but once such a pattern has been identified, we could then evaluate these measures for a match. We could look at the first row in such a match and output it, or we could refer to the match number. So is this the first, the second, the third, the nth match? And this is something that we could access. We could also identify or extract the tags that have been assigned to these matches, and all of this would then be collected in a table that could look like this and would be the equivalent of the peak and valleys that we have identified in our landscape. So all of this is present in the match recognize clause. A lot of functionality that we would have to manually reconstruct using window functions, but we could do it using window functions. Okay, so much for that. We are not yet at the end of our discussion of window functions. There's still one group of window functions, the so-called ranking window functions, left to discuss. This is the topic of the upcoming stuff. I hope to see you there. I will be around. So until then, bye.